Hello dear student, welcome to the next lecture in tensor analysis. In the previous videos, we have learned about notations and conventions used in tensor analysis, and also we looked into detail about the covariant, contravariant and mixed tensors. In this video, we will learn some of the algebraic operations that can be performed using tensors. As you are already familiar, tensors are represented mathematically as matrices. So every operations that are performed on matrices are performed on tensors. So in this lecture, what we are learning is just an extension of what you have learned in matrix algebra. You are extending your knowledge in matrix algebra to tensors and see what they are physically meant to. So in this lecture, we will be learning algebraic operations in tensors such as addition, subtraction, product, that is different types of products, inverse, transpose, and also different types of tensors such as symmetric and skew symmetric tensors, singular and non-singular tensors, and eigenvalues, and also about eigenvectors. Now let us start with addition and subtraction. Every product or every matrices that can be added by adding its components. You are familiar with matrix addition. Therefore, tensor addition is also similar to that of matrix addition. In matrix addition, suppose you have a matrix A, then it will be added to another matrix B to get another matrix C. And you all know that the first element of matrix A will be added to the first element of matrix B to get the first element of matrix C. That is, A11 will be added only to B11 and it will produce C11. Similarly, any element here, say A32 will be added to B32 to get C32. To add two matrices to get another matrix, it is important that these two should have the same order as well as the same rank. Therefore, adding two tensors also demand that they are of the same rank. That is, they have same number of indices and also they are of the same order, which means that they have to be defined in the same space. Therefore, if A plus B gives you C, then A, B, C are represented in the same space. They have the same rank and same type of indices and also the same number of dimensions. Same type of integers here I mean is that if A is a covariant tensor, then B should also be a covariant tensor, so the C should be a covariant tensor. A covariant tensor cannot be added to a contravariant tensor or a mixed tensor, even though that is Aij cannot be added with Bij. This is not possible. Therefore, the type of indices should also matter. In indices notation, we can write that Aij can be added to Bij is equal to Cij. Here both A, B and C are covariant tensors. In operational analysis, using operational analysis is a type of analysis where we operate a vector on a tensor to see its product. So, operational analysis we commonly use to determine the operation which is carried out by that tensor. So, in operational analysis we can say that given an arbitrary vector u, the sum of two tensors can be defined as A plus B operated by u will be equal to A operated on u plus B operated on u. And let us see an example. Here is an example from the fluid dynamics where sigma, you know, it is the total stress and tau is the deviatronic stress. The difference between the total stress and the deviatronic stress actually gives you the hydrostatic pressure. Here you know that the sigma is a second order tensor, and tau is also a second order rank 2 tensor. Both are rank 2 tensors. And P, the pressure is a scalar and it is multiplied with a rank 2 identity matrix. So a rank 2 sigma can also only be added or subtracted to a rank 2 tensor tau, and this should give you a rank 2 tensor. Therefore, this scalar, the hydrostatic pressure, is multiplied by a rank 2 identity matrix. The sum of two tensors always give you a tensor. Whether it's a vector or a tensor or a triad, it will give you the same order, the same rank. Now let us look into the product of two tensors. Using operational analysis, we can say that given an arbitrary vector u, the product of two tensors are defined as AB acted upon u will be equal to A acted upon B acted upon u. Hence, AB of u will be equal to A of BU. In integral notation, you can note that to multiply two matrices, the column of the first number of columns of the first matrix have to be equal to number of row of the second matrix. You are already familiar with that. So you will see this kind of symmetry over here in case of products. We will discuss different types of products in a short period of time. So keep that in mind. So AIK multiplied by BKL into UL is equal to AIK multiplied by BKL of UL. The direct product of two tensors is a tensor of rank equal to the sum of two initial ranks. That is, if you are taking direct product of two tensors, say rank 2 tensors, then the direct product will result in a rank 4 tensor. See, here A is a mixed tensor with index j and I, and B is also a covariant second order tensor, second rank tensor KL, and the product, its direct product, which is also known as the tensor product, will give you C is which has a rank of 4, that is IJKL. Here you are multiplying a tensor of rank 2 is taken tensor product with a tensor of rank 2, and you will get a tensor of rank 4. We will get into this in detail. Just to have a definition, a direct product of two tensor is a tensor of rank equal to the sum of the two initial ranks. And the direct product is associative, not commutative. That is, AB of u can be written as A of BU or the other way, but AB is not equal to BA. Now let us see different ways in which tensors or vectors can be multiplied. The first one is very simple. We can multiply a scalar to a tensor. We have seen this in our previous example where hydrostatic pressure is multiplied with an identity tensor. There the identity tensor was a third order second rank tensor. Similarly, we can multiply a scalar to a vector also. See, in the case of momentum flux, the density is multiplied by a vector. We know that the vectors are represented as in matrices as column matrices. This is how we represent a vector. If this is V, we can see that V, if it is of the order 3, then we will see it where V1, V2, V3. Then row V will be simply row V1, row V2 and row V3. Similarly, in the previous case we discussed, the Pi will be nothing but P0, 0, 0, P0, 0, 0, P, because I is an identity matrix. Here please don't be confused that we have two indices. This n is a free index, not a dummy index, because in summation convention we do not take the vector part. Here V is the vector. I can even represent it with a single underbar. This is also a vector. We don't consider the direction vectors in case of Einstein multiplication summation convention. This is just written as V is equal to Vm. While you're writing, make sure that you give an underbar, because you can broaden there. So you give a single underbar for a vector and a double underbar for a tensor. So multiplication with a scalar just scales the tensor or scales the vector to the scalar multiple. There is another way where two vectors can be taken product, and this is known as the scalar product. And here you are also familiar with the scalar product. So scalar product of two vectors A dot B using initial notation can be written as Aibj multiplied by its basis vectors Ai dot Ej. So we know that Ei dot Ej will actually give you delta Ij. Therefore, this product Aibj delta Ij will be equal to Aibi. If you have Aibi, then I is a dummy index. So what you will get is A dot B is equal to A1B1 plus A2B2 plus A3B3. Here I repeated twice, so I is a dummy index. This scalar product of two vectors actually results in a scalar, and for example work is defined by F dot S, where Fs both are vectors where work is a scalar. And knowingly or unknowingly, you have done scalar product using matrices also. See, you can define A. In the case of matrix, A is defined represented as a column matrix A1, A2, A3. Similarly, every vector is represented as a column matrix. But when you are taking a dot product, you are actually doing, what you are actually doing is A transpose is multiplied with B. That is, A transpose can be written as A1, A2, A3. A raw matrix A1, A2, A3 is multiplied by a column matrix B1, B2, B3. This is how you take the dot product. And now you can see that this will give you a result A1B1 plus A2B2 plus A3B3. So while taking a dot product, what you are actually doing is the transpose of the first matrix is multiplied with that of the second matrix. When you talk this out in terms of physics, we say that the dual the matrix, the vector of A in its dual space, you will learn more about dual space when you are learning about linear algebra in quantum mechanics. But just remember that for every space, every linear space, there exists a dual space. If A is represented as a raw matrix in it's a linear space. In the dual space, it is represented as A transpose. That is, in case of quantum mechanics, is we say that if A is a ket vector in its normal space, then in its dual space A is a bra vector. A ket vector defines the normal vector which is represented as a column matrix, where the bra vector is a vector, same vector represented as a row matrix. So in quantum mechanics, you have done this exercise. You have done A, B, right? You have done these types of exercises. So this actually means that the bra vector of A is multiplied with the ket vector B, which means that a row matrix of A, the state vector A, is multiplied with the column matrix of state vector B. This actually gives you a number. This will gives you a scalar, that is a number. So this type of multiplication is carried out in the scalar product or the dot product. Now another type of multiplication, that is cross product. You are also familiar with cross product of two vectors. You know how to do the cross product. To do the cross product, you will just take the determinant of ijk with components of A and components of B. So in indicial notation, I can write it as A cross B is equal to epsilon ijk, where epsilon ijk is called the Levi-Civita symbol or the alternator, multiplied by AJBK, and its normal matrices EJ cross EK, and in summation we will just ignore this and write A cross B is equal to epsilon IJK AJBK. Okay, this epsilon ijk, that is the alternator, will have a value plus 1 when ijk, both ijk are in the order 1, 2, 3 or 2, 3, 1 or 3, 1, 2. It will have a value minus 1 when ijk is in the anti-clockwise order. You can see that 1, 2, 3, 2, 3, 1, 3, 2 or 3, 1, 2. It is in the clockwise order. 1, 2, 3 is in the clockwise order. If it is in the clockwise order, then epsilon ijk will give you plus 1. If it is in the anti-clockwise order, then epsilon will give you a negative 1. If any of these are equal, that is epsilon will give you 0 if I equal to j or j equal to k or k equal to 1. If any of these are equal to, then this alternator will give you a value 0. This is similar, this is also a tensor, and it is similar to our we have already learned about Kronecker tensor, similar to a Kronecker delta tensor, another type of tensor called alternator. So A cross B can be defined as alternator ijk ej bk. Here also you can see that I is a free index, j and k are dummy indices. In notation we don't use this, we will just write ijk aj bk. Example for this is our maybe our angular momentum vector, where r cross p angular momentum vector are calculated using the cross product, and cross product of two vectors result in another vector in a dimension perpendicular to the initial vectors. Hope you are clear with what we have learned so far. So we are stepping into another step, that is a dyad or a tensor product. Hope you have understood what we have said about the scalar product, that is the dot product. In case of dot product, in matrix what we do is we take the transpose of the first vector, multiply it with the second vector, so that our answer is a scalar. That is, two multiplication of a vector will give you another with a reduced rank. Similarly, if you multiply A with the transpose of B, what you will get is a tensor. And if you multiply vector A with transpose of B, that is, in this case vector A is represented as a column matrix itself, where B is represented as the row matrix. If it is A1, A2, A3, B1, B2, B3, instead of getting a scalar, you can try multiplying this. What you will get is A1, B1, A1, B2, A1, B3 up to A3, B3. This is what you are gonna get. So just try this. When you multiply a vector with the transpose of another vector, what you will get is a tensor. So this type of multiplication is known as a tensor product or a dyad. So a dyad of two vectors will actually give you a tensor. That is, a dyad of two tensors will give you a tensor with a higher rank. And here you can see that A cross B, the dyad, can be represented as AIBG, and in summation convention we will get rid of this. So here I and J both are free integers, so both I and J have to flow from 1 to 3. Therefore you will get 9 components, and these 9 components are in the tensor form. For example, if you are taking tensors, say A tensor is being tensor producted with a tensor B, what you will get is C, which has if this tensor is rank 2 tensor and B is also of rank 2 tensor, the C will be rank 4. This is what we have learned a few slides below, that is also called the direct product. If we take direct product of two tensor, the resultant tensor will have a rank sum of the rank of the initial tensors. You will come across many tensor product when you learn things in the Hilbert space, that is in quantum mechanics. Also, the graded vector fields are tensor products. We will take tensor products. We will see many tensor products in quantum mechanics also. Now let us learn another type of tensor, that is a vector multiplied by a tensor. While defining tensor in our first video, we have said that tensor can be used to map a vector. That is, when I multiply a vector with a tensor, it will give me another vector. So another vector having another direction and also another magnitude. When you multiply a scalar, what you're gonna get is just a scalar multiple of the same vector. But if you are multiplying a tensor, what you're getting is another vector. I will take the same example which we have done in our first video, that is magnetic field intensity in the free space. B is a vector, H is a vector. where mu in the anisotropic medium, the magnetic permeability in an anisotropic medium is a tensor of rank 2. Therefore, when I multiply h with the vector h with the tensor mu, what I will get is b. Here also you can see that mu vector is multiplied with the h vector, and this kind of multiplication, you are familiar with this kind of multiplication in vector and matrices algebra, and you know that it will give you a column matrix, so it is indeed a vector. Consider another example. This is from fluid dynamics when we are dealing with the contact forces on the surface. So to find the tension on the surface, we will multiply the total stress as taken dot product with the that of our normal to the surface. So we can write that in initial notation sigma ij ei ej. Since it's a vector tensor, we have two different base vectors, and in a normal to the surface, so normal to the surface will be in the ek direction, nk ek. When we are taking single dot product, we will dot ej and ek, and what will result is in delta jk. If we have delta jk, we can replace all k with j, and the result can be written as sigma ij nj ei. Using summation, we can get rid of this and write sigma ij nj. Here j is the dummy, and this is, say for I is equal to 1, I can write this tension can be written as sigma I1 N1 plus sigma I2 N2 plus sigma I3 N3. That is sigma I1 N1 I2 N2 I3 N3 will give you the product. So here come to the quotient rule. This is just the contrary of what we have said in the product with tensors and vectors. This rule says that if aij bi is a vector, that is, if this product gives you a vector where bi is a vector, then aij have to be a tensor of order 2. Just the opposite of what we have said so far. Now another type of product is the dot product of two tensors. With using tensors, we have learned that tensors can be added. Now we have learned a lot about vectors. So similarly to how we dot product two vectors, we can dot product two tensors. If we dot product two tensor, the resultant will be a tensor. Consider two tensors A and B. When I dot product it, say APQ, EPEQ, here EPEQ. These are tensors, either write in the bold letter or with our underbar. BIJ, EIEJ. So when I take single dot product, what I will do is EQ will go with EI. So EQ dotted with EI will give me delta QI. So using delta QI, I can replace all the i's with Q and write APQ, BQJ, EPEJ. Using summation convention, I can get rid of this and write my product as APQ, BQG. Therefore, here we can see that you have one dummy index and two free indices. Since you have two free indices, this is a tensor of rank 2. This will result in another tensor, but you can see that APQ is multiplied with AQJ. Therefore, the transpose of A is here multiplied with B. Not A is directly multiplied with B. The transpose of A is multiplied here with B. You can try it for any. Suppose try it if it gives you, suppose it gives you C, then try it for C 3 2 and see what it gives you. And you can see that the transpose of A is here actually multiplied with that of B. So you can take dot product of two tensors and it will result in another tensor. You have already seen you can take the tensor product of two tensors and this will result in another tensor with a higher rank. Now you can take the double dot product also. If you take a double dot product of two tensors, this will result in a scalar. For example, is a viscous dissipation or the strain energy from fluid dynamics. To calculate the viscous dissipation, actually viscous dissipation is a scalar. It is obtained by taking the double dot product, also known as the contraction, double contraction of the total stress sigma with the energy E. So when we take double dot product using initial notation, I can write sigma PQ is equal to E into EP EQ double producted with EMN EM EN. So when I take double dot product, EQ is dotted with EM and EP is dotted with EN. When I dot product EQ with EM, I will get sigma QM, and EP with EN I will get sigma PN. So I can easily replace all the Q's, all the M's with Q's and also all the N's with P's and write sigma PQ E QP. Here both P and Q are both P and Q are dummy indices, so they just add over. You don't have any components, they just add over. Suppose this is a three-dimensional case where P and Q run from 1 to 3, then this answer will be just sigma 11 E11 plus sigma 12 E21 plus sigma 31 E31 plus etc. plus 9 terms. You will have 9 terms and the answer will be a single number, that is a scalar. So in case of matrix, what you will do is you will take A transpose B. Similar to what you have done here, you will take A transpose B and take the trace of the resultant matrix. You know how to take the trace of the resultant matrix, right? So you will take A transpose B, calculate A transpose B and take the trace as a product of the diagonal elements. So let me introduce the term contraction to you. Here you have seen that you have a tensor here. You have a tensor here and you have reduced it into a scalar. Similarly, look over this expression. Here in this expression, you have 4 different indices. Okay, A have a rank 2 and B also have a rank 2. So here what you have is 4 different indices. Now when you dot product this, you will get something which can be reduced. So your reduced answer was A PQ B QJ. Here you have only 3 indices. When you started, you had A PQ B Ij. Here you had 4 indices. But when you have done something, when you are done an operation, it reduced to 3 indices. So that kind of operation which actually reduces the base vectors is called the contraction. So when you do a single dot product, it is reduced by 1 and it is known as contraction. Here you have done double dot product, so it have reduced your number of base vectors into 2. Here you have only p and q as base vectors, so it is called double contraction. So contraction is a method of reducing the order of a tensor by identifying any two of its indices. Here we have identified q and I. Here we have identified q and m and also p and n. By making any two of the indices similar, which we actually do using the dual space. That is, we use the covector formation of the dual space, and we can reduce the number of base indices which is needed to represent a tensor. Now let us see what is an inverse of a tensor. You are familiar with the inverse of a matrix. So the same case, if a tensor A, an inverse of a tensor A can be written as A inverse. It satisfies the property that is A inverse will be equal to I. In initial rotation, I can write A Ij, A Kj will be equal to delta Ij. See, this have to be same. And in matrix formation, you know how to find the inverse of a matrix, right? The adjoint of A is divided by the determinant of A. When determinant of A is equal to 0, this means that the inverse doesn't exist. This exists only for the determinant not equal to 0 case. So inverse of a second order tensor is also a second order tensor. On the basis of whether the inverse of a tensor exists or not, we can classify the tensors as singular and non-singular tensor. So for every tensor A, if its inverse exists, such tensors are known as invertible or non-singular or non-degenerate. By definition, an n by n tensor A is called invertible or non-singular or non-degenerate if there exists an n by n tensor B such that AB is equal to BA is equal to IN. Here I denotes the identity tensor, n by n identity tensor, and B is written as A inverse such that it will satisfy this condition, that is A inverse is equal to I. This invertible tensors, the non-singular tensors, actually play a greater role in physics. That is, if a tensor is invertible, it is transformed by a sequence of elementary row operations or column operations. It can be transformed using elementary row operations or column operations. You have done row operations and column operations during matrix algebra. This in physics just means that we can transform these tensors. While defining the tensors, we have already said that tensors are invariant, something which is invariant under transformation. So on changing the basis can be done. Actually all these columns, every column or every row represent its basis vectors. So when we are changing the row or column, we are actually changing the basis. So this changing of the basis can be carried out. Another property is it will have n pivot positions. So in matrix analysis, pivot position is one particular element about which all the operations are carried out. Hope you know the pivot. Remember the pivot element. We will just make one element stationary, and about that element we perform row operations and column operations. So in terms of physics, I can say that any such position or any such point about which all these symmetry operations are carried out, the axis of symmetry or point of symmetry. So here if you have a non-singular tensor, then you will have n point of symmetry. Also, if your tensor is non-singular, its rank will be equal to its dimension. Its null space or the zero vector exists. The null vector, the zero vector exists. Its columns forms the basis. For example, the identity tensor is a non-singular. You know that it's a non-singular tensor. So can be written as 0, 1, 0, 0, 0, 1. Here this 1, 0, 0 is actually the x basis. Similarly, 0, 1, 0 is the y basis. The column matrix 0, 0, 1 actually represents the z basis. So all the columns forms the basis for the space. And talking about the eigenvalues of this matrix, its eigenvalue exist. That is, 0 is not an eigenvalue. Eigenvalue has some more physical meaning than just being a value. If eigenvalue of an operator exists is not 0, which means that that operator exists in that space. For example, its energy or momentum, and you calculate the energy or momentum using its operator, and you get its eigenvalue at 0, then means that that particular system doesn't have a momentum, or particular system doesn't have an energy. You are familiar with the transpose. Have to take the transpose of a tensor. Transpose by matrix is taken by interchanging the rows and columns. So using operator method, I can define a given arbitrary vectors u and v. Transpose of a vector is defined as u dotted with av is equal to v dotted with a transpose u. So transpose of a tensor is also a tensor. Transpose of an identity matrix is that matrix itself. And you can actually prove that the transpose of an identity matrix is itself by just replacing a with I, and you can do it on your own. Now, with what we have learned with the transpose, using transpose we can actually classify tensors into symmetric, skew symmetric or orthogonal tensors. So if a tensor is symmetric, then its transpose and itself will be equal. That is, if A is a tensor and A is equal to A transpose, then A is called a symmetric tensor. In initial notation, I can write that Aij is equal to Aji. Examples of symmetric tensors are the metric tensor, the Einstein tensor, the Ricci tensor, and many of the material properties are defined in the symmetric tensor fields. Similarly, if an arbitrary tensor A is called a skew symmetric or an anti-symmetric tensor, then A will be equal to negative of A transpose. In initial notation, I can write Aij is equal to negative of Aji. And examples of skew symmetric tensors are all scalars and vectors are skew symmetric. The electromagnetic vector F mu nu, we have done this in our first lecture video, hope you remember. And also whatever comes in the pseudo-Riemannian manifold, you will learn this in your general relativity course, are also a skew symmetric tensor. Now, not everything in the pseudo-Riemannian manifold, just some tensors such as a volume which is defined in it. Okay, another tensor is the orthogonal tensor. So orthogonal tensors are tensors which can be defined as A transpose is equal to I, or A transpose A is equal to I. In initial notation, I can write that AJK is equal to AIK, that will be equal to delta Ij. AKJ is equal to AKI will also give you delta Ij. This implies that A transpose, if A transpose is equal to I, then A transpose is equal to A inverse. So examples of orthogonal tensors, we have seen orthogonal tensors when we are making transformations between spaces. We have done that already. The rotational matrix, we have done that also. These all are orthogonal tensors. The symmetric tensors are denoted by the symbol S, antisymmetric by W, and an orthogonal tensor by a letter capital Q. So any arbitrary second order tensor A can be decomposed into a symmetric form and an antisymmetric form. We have done this already in your matrix formation. That is, A can be written as S plus W, where the symmetric form S is equal to A plus A transpose by 2 and W is equal to A minus A transpose by 2. You can prove this using any symbol matrix you can find. Try this. We have already done this in your elementary classes. So in initial notation, it is written as Aij is equal to Sij plus Wij, where the symmetric part is A plus A transpose by 2 and the antisymmetric part is half of that is A minus A transpose. This kind of decomposition of a single tensor A is called an additive decomposition. There is another decomposition known as multiplicative or polar decomposition, which is using the orthogonal tensor Q. Therefore, if A can be decomposed as one orthogonal tensor and one symmetric tensor. Here orthogonal tensor Q transpose is equal to Q inverse, and the symmetric tensor S will be equal to S transpose, and symmetric tensor similarly you can find with A plus A transpose by 2. You can also prove this using any simple matrix. This type of decomposition is called multiplicative or polar decomposition. There is some other kind of decomposition called spectral decomposition. This is not much in your syllabus. We do this using characteristic equation, and in matrix, in elementary matrix classes, you have done that also. Maybe not just taken the term spectral decomposition. Now towards the end, we will learn about eigenvalues and eigenvectors. So eigenvalues and eigenvectors actually hold a lot inner meaning in case of when we are dealing with physics. So when you have, suppose you have an operator acted upon a state vector. So in quantum mechanics, it is acted upon a state vector. Then you will get an eigenvalue. So if you get an eigenvalue which says that the operator actually exists. Suppose you have a Hamiltonian operator. Every operators are matrices. We know that operators are defined as these kind of operations will give you operators, that is transpose of something, normal vector, this A is multiplied with the transpose of B. These kind of operations are gonna give you operators. So operators are already matrices. So suppose you have a Hamiltonian operator here and you act this Hamiltonian operator on any state vector. If you act Hamiltonian operator on any state vector and this gives you some scalar with the same state vector, then you call this state vector an eigenvector of this Hamiltonian operator. This means that this Hamiltonian operator as well as this state vector are actually defined in the same space. Suppose we have another example. Let's say you are measuring distance. If you are measuring distance in a state, and you will get some value with the state itself, this means that this whole thing is defined in the same space. For example, in the momentum space, if you are going to measure distance, you will not get something like this. In the position space, you are measuring position, then you will get an exact position value. So this value will actually give you the exact position, say 3 meters, so 3 nanometers will give you the exact position of that state. So mathematically, we can say that if any vector can be mapped to itself in using a tensor, then we call that vector an eigenvector. We are familiar with the eigenvector equation, that is an is equal to lambda n. Here you can see that this vector n is mapped to itself using an operator, using a matrix, a tensor. Then this vector is known as the eigenvector, and the factor to which it is projected or scaled is called its eigenvalue. So here an is equal to lambda n. Here n is the eigenvector and lambda is the eigenvalue for that corresponding eigenvector. You can find eigenvectors and eigenvalues mathematically by taking the determinant of this equation, that is determinant of an minus lambda n is equal to 0. By equating it to 0, you can find the eigenvalue. This is a third degree polynomial equation. You usually do this. If you have a matrix A, what will you do is take the determinant of A minus lambda and equate A minus lambda I and equate it to 0, and you will get values for lambda. So all the values you get for lambda are its eigenvalues. So eigenvalues can be 0, can be positive, can be negative, or can be complex values. And to find the eigenvector, what you will do, you will just trace back. You will get give all the numbers over here, that is A minus lambda I. This matrix will now be multiplied by n and equate it to 0, and you will find all the eigenvectors for corresponding eigenvalues. For symmetric tensors, we can find that all its eigenvalues are real. I said that eigenvalues actually says to you that whether a particular observable, a particular physical observable is actually an observable or not. If it gives you real eigenvalues, then it is a physical observable. Also, if it is not 0, then it is observable in that particular space. So eigenvalue of symmetric tensors, and you can find in quantum mechanics that every observable such as energy operator Hamiltonian h, the momentum operator p, the spin, the angular momentum, or anything, any physical observable are symmetric tensors, and they will give you real eigenvalues, as well as if they are symmetric, then their eigenvectors will be orthogonal to each other. So eigenvalues are real. That means it can be negative, positive, or 0, but cannot be complex. Therefore, modulus of lambda I also always have to be greater than 0, and its eigenvectors will be orthogonal to each other. So its eigenvectors, say ni ng will be delta ij. They will be orthogonal to each other. So in this video, we have learned about all the algebraic operations that can be performed on the tensors, and also different types of tensors such as symmetric or invertible, etc. So these are my references. Thank you.